All right, welcome back. This time we're going to look at an example which seems like it's really not going anywhere. And sometimes we just have to uh, try a different approach. And that's what we're going to run into in this problem here. So part of the problem that that's going to be caused here is due to different angles in our two expressions. So that's part of the issue here. But we'll see what happens, and I'm going to show you there is a way to manage a problem like this. So this is limit as x approaches pi from below of cosecant x plus x all over tangent of x over 2. So let me draw in my unit circle here because I want to think about what values we're taking on here as we approach pi. So get myself a circle here. It's pretty close. Actually, hold on here. Need to move that down. There we go. Okay, so there I have a unit circle. And we're approaching pi, so that would be, of course, over here. So on the one hand, I'm taking on values just a little bit smaller than pi, and that will apply for the numerator where we're dealing with x. We're approaching like that. So as we approach pi, cosecant, which is the reciprocal of sine, sine's approaching 0. Sine is positive there. So 1 over 0 would, of course, be approaching positive infinity. So we're dealing with an infinity in the top because plus pi isn't going to make a difference. In the bottom, though, our angle is x over 2. Our angle is x over 2. So that means as x approaches pi, that x over 2 is actually approaching pi over 2. So with tangent, we're actually approaching pi over 2. Tangent is sine over cosine. So what's going to be happening is cosine's approaching 0. We're positive in the first quadrant there. So cosine's approaching 0, sine's approaching 1, so it's approaching 1 over 0. So the bottom is also going to be infinity. So this is an infinity over infinity. So our initial process is let's try L'Hopital's rule. So we have infinity over infinity. So let's differentiate the top and bottom. So we do that. So limit as x approaches pi. Then we differentiate. Derivative of cosecant is going to be negative cosecant x, cotangent x. Derivative of x would be plus 1. Okay, in the bottom, we would do the derivative of tangent of x over 2. So derivative of tangent will be secant, derivative of x over 2 would be 1/2. So this is going to be 1/2 secant squared of x over 2. So let's take a look at that one. Well, as x is approaching pi, as x is approaching pi, cosecant is still approaching infinity. Cotangent is cosine over sine. Cosine is approaching negative 1. Cosine is approaching negative 1. Sine is approaching 0. So that would be a negative infinity. So we're going to have the negative of infinity times negative infinity. And all that's going to be infinity, and then plus 1's not going to matter. In the bottom, we have 1/2. As we approach pi, then secant, we're talking about approaching pi over 2. Secant's 1 over cosine. Cosine is approaching 0. So that's another infinity. So Once again, that didn't help. We're now dealing with another infinity. So we're, once again, infinity over infinity. So we try L'Hopital's rule another time. See where that helps us. See where that gets us. So limit as x approaches pi from below. And then we do the derivative at the top. That would be negative cosecant times the derivative of cotangent. Derivative of cotangent is negative cosecant squared. So negative cosecant times negative cosecant squared. We'll make that be cosecant cubed of x. Plus the cotangent times the derivative of negative cosecant. Cosecant's derivative is negative cosecant cotangent, so it'd be cotangent times that, so that's actually going to be plus. And that would actually be cosecant x cotangent squared x. Okay. Things aren't looking very good on top here. Things are not looking very good on top here. Just so you're aware. This is still going to be an issue of infinity and another issue of infinity. It actually might be infinity minus infinity even. It's not fun. It's not fun. The bottom, what's going on here? Well, we have to do the derivative of that stuff. So that's going to be 1/2 times the derivative of secant squared, which would be times 2 times secant of x over 2 times the derivative of secant, which would be secant of x over 2 times tangent of x over 2 times the derivative of 1/2 times 1/2. Okay. At this point, I'm just like, ugh. You know, what in the world? It's just awful. It just keeps getting worse. So part of the problem here is right now we have this mixture of angles. In both going at pi for the top and pi over 2 for the bottom stuff. Just keeps all this stuff going over and over and over again. At some point we might think, you know what, I got to do something with it. But again, one of the big problems is the angles. Angles being different. Well, there's a little known trig identity, which probably doesn't get a lot of attention, but it's actually very useful here. And that is that tangent of a half angle can actually be written as 1 minus cosine x over sine. And also as sine x over 1 plus cosine x. Either way, actually, it can be written as either one. This is a half angle identity. You can actually get between the two versions of it by using the idea of multiplying by the 1 plus or minus cosine. So if you took the second one here and you were to go in and multiply by 1 minus cosine x over 1 minus cosine x, basically what would happen is that would give you the 1 minus cosine in the top. In the bottom, you'd get 1 minus cosine squared, which would become a sine squared. That would cancel one of the signs on the top and leave you at the sign on the bottom. Okay. So either version of this identity works. We're going to choose a particular version of it. I'm actually going to take the first version because I think it works better for what we need to do here, as we're going to see in a moment. So that's going to allow me to take from an x over 2 angle over to an angle just involving x. And that'll actually help me be able to work out this problem. So going back from the original problem now, which was limit as x approaches pi of cosecant x plus x over tangent of x over 2. I'm now going to substitute in for tangent of x over 2. I'm going to substitute in for tangent of x over 2. So limit as x approaches pi from below of cosecant x plus x now over 1 minus cosine x over sine x. And so then what I'm going to do is I have that complex fraction there, so I'm going to multiply both top and bottom by sine of x. Okay, and watch how that's going to transform things for me. Limit as x approaches pi from below, sine times cosecant. Well, sine and cosecant just cancel each other out. It'll be 1. Plus sine times x, so it'll just be x sine x. And in the bottom, I'm going to have just 1 minus cosine x. Okay, so I've made that change. And now notice that as we approach pi, there's no longer an infinity over infinity issue. We've actually resolved it already with this complex fraction idea here, when we multiplied through by sine over sine. Because now the top, I can just let x become pi, and that will just be 1 plus pi times 0, which will be 0, over 1 minus a negative 1. And so it turns out, all told, this is 1/2. So L'Hopital's rule is, again, not always the be-all, end-all. It will work everything out for us. And this example kind of shows that we needed something else. We needed something else. It was actually this identity here. That we actually needed. Now, I would not present you with a problem like this on an exam, expecting that you memorized this identity. I just wanted to show this to you as an example. You could come across something similar in the homework where you needed to make use of something like that. But just to kind of show you that L'Hopital's rule isn't the bee's knees. It isn't the thing that's always great, works. It works a lot of times, but sometimes a softer approach, a different approach needs to be taken.